In the first two examples, first two match problems, our substitutions were all relatively straightforward. We found the interior function, and then we were able to replace kind of the remaining portion of that problem with just du by itself. In match problem 5, now we're going to look at some cases that are a little more complex. The substitutions are going to require a little bit more thought and manipulation on our part, but we'll see that as we move through these. They still start off the same way. What we have is negative 3x as our interior function. So we can let u equal negative 3x. And now taking the derivative of both sides, we'll get du over dx equals negative 3. And then multiplying both sides by dx gives us du equals negative 3 dx. At this point, what we want to do is replace dx with du. But we have a little bit of a problem here because du is equal to negative 3 times dx, but we don't have negative 3 times dx, all we have is dx by itself. There are a couple different ways to proceed at this point, but the way I do this is I look at what I have remaining. So the only thing that I have to substitute in is just dx, so I need to get this expression dx by itself. So to do that, I'll divide both sides by negative 3. Which means that now I have du over negative 3 is equal to dx. So negative 3x we swapped out with u, and dx we'll be able to swap out with du divided by negative 3. So our new problem becomes the integral of e to the u and then in place of dx, we have du over negative 3. Now, initially that looks a little strange until you realize that dividing by negative 1/3 is the same as just multiplying times 1 over negative 3. And that's just a constant multiple. So our properties of integrals let us bring that constant multiple out in front. So all we're integrating is just e to the u, and whatever that result is will be multiplied by negative 1/3. So we have negative 1/3 e to the u, since the integral of e to the u is e to the u, plus some constant c, or negative 1/3 e to the negative 3x, replacing u with that original substitution, plus some constant c. So again, the overall process here was the same. We want to rewrite this original problem in terms of u and du. We just had to get a little more creative with this substitution of du, since we didn't have negative 3 dx showing up in our problem exactly. So those can be a little more confusing. Fortunately, we've got several more examples to take a look at here. So here we have our interior function is x, x squared minus 9. So we'll let u equal x squared minus 9. Taking the derivative of both sides will give us du equals 2x dx. So I'm starting to skip over some steps. That would be du over dx, and then we'd multiply both sides by dx, but that pattern's the same each time, so I'm just going to skip over that step and just rewrite this as du equals 2x dx. Again, I have a problem where I don't have 2x dx to substitute out. All I have to swap out is just x times dx. So I can get x dx by itself if I divide both sides by 2. And that means in place of x dx, I can write in du over 2. So our integral becomes the integral of 1 over u, and then times du over 2, where du over 2 has again replaced x times dx here. So we can use those properties of integrals again to rewrite this as 1/2 times the integral of 1 over u du, and now we have one of those simple integration cases again. This is just going to be 1/2 times the natural log of the absolute value of u plus some constant c, which is 1/2 times the natural log of x squared minus 9 plus some constant c. So again, if the first few examples made sense, now we're just getting a little trickier with these substitutions, doing a little bit of additional manipulation there. And let's look at one more example of the same type of problem. So our interior expression here is t cubed plus 4. So we'll let u equal t cubed plus 4, which means du is going to be equal to 3t squared dt. Now, what we have in our original problem left over is 5t squared and dt. So the 5 doesn't match up with 3, so really all we have to swap out is t squared dt. So I'm going to kind of carefully select the t squared there, but not 5, and select this dt. So in place of t squared and dt, which we have here, we could substitute in du over 3 equals t squared dt. So t cubed plus 4 is going to be what we substituted for u, and then in place of t squared dt, we'll substitute in du over 3, meaning our new problem is the integral of 5, since that 5 didn't go anywhere, we didn't make any substitutions for it. 5u to the negative 2, and then in place of t squared dt, we're going to replace that with du over 3. And then again, pulling our constant multiples out front, this is 5/3 times the integral of u to the negative 2 du. So this will become 5/3 times u to the negative 3. I'm sorry, let's do that correctly. So if we have a negative exponent, we're still adding 1 to that. So that's going to become u to the minus 1 over negative 1 plus c, which is just going to be negative 5/3 t cubed plus 4 to the negative 1 plus c. Or if we wanted to rewrite this with a positive exponent, this would be negative 5 over 3 t squared plus 4, t cubed plus 4, plus some constant c. So again, either of these two answers would be completely acceptable to me. The only difference might be if MLP, the homework system, wants that rewritten with a positive exponent.